Usually you take the exponent and times it by the other exponent. Well, there's
Okay, so these here.
Three exponents, so if you just take all three numbers and time them together, that'll work. All right, let's try a couple variables to that.
All right, so for these here.
It's just A, I got the other two.
So A has got 120 times x to the third times x. So remember, anything next to each other like that is just multiplication. And you can multiply in any order you want. So here, it makes sense to combine the x's together. And that's x is just the same as x to the first. So how many x's are being multiplied?
4.
4 of them, yeah. So this would be the same thing as 120 x to the fourth power.
All right. See, I messed up on that. I thought it was the x was just x equals. They wanted to know what that and then x equals.
Yeah, no. So there's a multiplication here. Yeah. So that's why we were
I
just
thought
simplifying
the
that
x was
separately.
taken out completely, and they wanted to know what the other two were going to be written.
And just clean that up there.
All right. Next.
You said number 3.
Yeah.
Okay.
D.
3D. Okay. So we got a couple of rules going on here, and order of operations still applies. So there's nothing to do inside here, but we got to do powers before we can multiply. So I'd have to clean out x to the fourth squared. What's the rule on that? Power to a power times the, yeah. So that is going to be x to the power 4 times 2, which is going to give me an x to the 8. And then I still have that x cubed hanging out waiting to be dealt with. So now we have two things with the same base being multiplied. What's the rule on that one? Add them up. Yeah, so that would be x to the power 3 plus 8, which is x to the 11 on that one.
I thought that it was all times. So why is the 3, if x3 times x is x8, why is the 3 just plus 8, not times?
Well, this is just a shortcut right here. And the bottom line is the rules for exponent means this means you have 3 x's written out.
Yeah.
And then the 8 means you have 8 x's written out. So how many x's do you have altogether? So there's 11 of them. So it's just a shortcut, so you don't have to do that because that's a pain in the butt. What if there are 100 of them? You do not want to write those out. So the bottom line is this says there's 3 of them multiplied. That one says there's 8 of them multiplied. So altogether, there's going to be 11 of them multiplied out. The shortcut there.
All right, 4 was C.
4C? Okay.
All right, so let's see, we are using our, so this again is using that multiplier thing, like the example they give here is going to be helpful, that if there's a 9.4% tax, you're going to pay more. And so it's down here. So adding on the 9.4 is it's the same thing as ending up with 109.4% later. So that's an important rule. All right, so company is planning on expanding the number of workers in each department by 25%.
The reason why it was different is the third one, the one that the C was where it was taken away. And so I was trying to do the same formula with it was like a minus.
Yeah,
1.
so yeah, discount means it's a negative rate.
Yeah.
But here we've got, let's see, we're expanding. So
Yeah.
that's an increase, that's a positive rate.
C, though.
Oh, you said the question was C, I'm sorry, okay, I don't know why I said B. Yeah, so C is a negative rate. So that's a negative 20 right there. So let's see, just after one discount. So on that one right there, we've got 20% off. So that means our rate in this case is a negative 20%, which is negative 0.2 as a decimal. And comparing that to 1%, we always take, 100%, we always take 1 plus r. R is negative here, so I get 1 plus negative 20%, which is the same as 1 minus 20%, which gives me 0.8 or 80%. That's the multiplier.
That's what my problem is.
Yeah, so that means if you get 20% off, you pay 80%, is what we figured out there. So here they want us to apply that by saying if the current price is P, what's the new price? What do I do to the current price to get the new price? Yeah, it's 80% of whatever the current price was. Oops, that's supposed to be at 0. Yeah, so this is 80% of P is what they're looking for there. And the one above, that's a 25% increase. So what do we multiply W by there? The 25% up. Up, that would be down, we're going up. So it'd be 1 plus 0.25, so that would be 1.25, because we're expanding is an increase. This one up here says a restaurant's gonna raise all their prices by 2%. So what do we multiply the current prices by to get the new prices if we're going up by 2%? 2% is a decimal as well. 0.02, and then I had to add that on to 1, so my multiplier, my new price is going to be 1.02. So that represents a 2% increase. 1 is 100% where we start. Here's a 25% increase. 1 is 100% where we started. Okay, so whenever I put the 1 on there, that gives me the new amount, not the change, but the new amount. And that's the big thing we're working with in this chapter. Here we lost from 1% by 20, so that took us down to 80. So sometimes we go up, sometimes we go down. It's always with respect to 1, which is where you start. All right. Other questions on homework 4.1?
3 and 4, which I think are both the same, so just one of those.
One of those.
Show me one within 5, 6, and 7. I think they're both the same.
Okay. 4.1 homework. Which one again? 3?
3 is 4.
I
had a question about that. How is this different?
How is linear different from exponential? So we went over that yesterday. Yeah, so an exponential model has a relative growth rate. A linear has what? What is it? It's absolute. What were we gonna say? Sure. Okay. Yeah. So it has a constant slope, which is an absolute change. It's always the same amount. Okay. Whereas exponential, it's a percent change. Those are the big differences. Okay, so number 4, here we've got compound interest. So we want to complete this table here. And this is a good spreadsheet one, so I'm going to throw this into a spreadsheet too. Complete the table below to compare the amount you would have. You take $1,000, 5% simple interest, compared to $1,000, 5% compound interest. Okay, let me bring this into table first, and then we'll bring it into spreadsheets. Oops. All right, so differences in formulas, and that this is stated above the problem also. Simple interest. The interest amount that you get is just your principal times the rate times the time, and that's it. And then we can take that and we can add it back on to what we started with. So this kind of thing is where you put $1,000 in the bank for a certain amount of time, maybe they say 2 years. At the end of 2 years, they don't give you any interest until the end of 2 years. Then what they do is they give you your money back plus the interest, and that's the end of the story. So that's kind of how simple interest works.
Compound interest is if they're compounding annually, that's where we have our fancier formula. So that would be, we take the principal and we take 1 plus the rate, our multiplier, and raise that to the amount of time that goes by. And that's the compounding, that power. So for example, I'm just going to focus on 3 years here, and the other ones are pretty similar. For simple interest in 3 years, they're going to give me my $1,000 investment back, and then they're going to calculate my interest. How do we calculate interest again? Just interest. Just principal times rate times time. So my interest part is going to be that whatever I invested times my rate was 5% here. How much time has gone by? In this particular one I'm looking at, row 3 years have gone by. So there's no compounding here, there's no powers. It's just principal times rate times time is your increase, add that onto where you started. Okay. So I'll whip out a calculator and get that number, write it down. So my interest, 1,000 times 5% times 3 years have gone by, simple interest. Google says that's $150. So that means at the end of 3 years with a simple interest account, then I'm going to have $1,150 with simple interest. With compound interest, they have to, at the end of each year, they have to stop and say, okay, you have this much more money in your account. And they have to keep repeating that. So we have the powers there. So for compound interest here, for 3 years, I'm going to have my $1,000 that I start with times 1 plus my rate, 5%, raised to the power of 3. Notice here I'm raising to the power of 3. Here I'm only multiplying by 3. Slightly different scenario. Multiplying is different than an exponent, so I should get a different result. So 1,000 times parentheses 1.05 is my new multiplier raised to the power of 3. Calculator says I'll get $1,157 and let's call it 63 cents. And again, what's the difference here? The difference is that with compound interest, you get a little bit more money here, and that collects interest. Then you get a little bit more money here, and that collects interest. So with compound interest, your interest collects interest. With simple interest, nope. There's no intermediate step. It's just an end number. And using powers with compound interest allows us to skip calculating those intermediate steps. We just jump right to the chase. Simple interest versus compound interest. All right. So by the way, simple interest, that's like linear change. If we graph those numbers, it would just be a straight line, whereas the compound interest is going to curve up. As time goes by, we're going to get better and better off because our money keeps collecting more money. All right, let's see. Number 5, 6. All right. So this is the same information right here that was in the beginning of your worksheet 1 about what is a certificate of deposit. So if you didn't read that in the worksheet, you get a second chance to read it. All right, so let's see. We have Lorenzo and Michael each decide to invest in a mutual fund. They choose mutual fund that has an average annual return of 5.6% over the last decade. There's no guarantee the fund will continue to earn the same rate, but we'll just use that as an estimate for the future. Use the information below to estimate how much each man will have when he retires to the nearest dollar. So Lorenzo is going to invest $2,000 one time, and when he is 25 years old, and he's going to retire at 65. Michael, 5,000, he's 45 now, and he's going to retire at 65. So we want to figure out how much they get at retirement and how much interest they earn altogether.
And I gotta remember to go back and do that other problem in a spreadsheet too for fun. So let's see, we'll do a screenshot. So whip out your calculators. I'm gonna need some help here. Or a spreadsheet. But first I'll do it on paper with a regular calculator, and then we'll do this one in the previous problem with a spreadsheet. All right, so let's see, double check. I think we're just getting yearly interest, is that right? Yeah, it's compounding annually, all right. As opposed to monthly, like some of the other stuff we did.
So our formula, what was it, 6.5% on average? Is that what it said?
That was what?
5.6, sorry, backwards.
All right. So our APR here is 5.6%. As a decimal, that's 0.056. 5% is 100, so the 5 has to be in the 100th spot. Our APR, we're compounding annually. That's important. All right, so then let's see. They're both going to retire at 65. Lorenzo is 25, so what's that? He's going to have it in there for 40 years. So 40 years for him, and let's let Michael be red. Michael is 20 years. And our formula for stuff like this, the new amount A is going to be the initial amount P, the principal, times 1 plus the rate to the time, and the time and the rate have to be over the same period, right? It's an APR, the collecting interest yearly, so we're good there. So for Lorenzo, his new amount is going to be 2,000 times 1.056 raised to the power, he's the one going for 40 years. So we need to whip that into a calculator. So if everybody could help me check this number, see if we agree. $17,000? Anyone else getting a number like that? 17,684.25. All right, so there's Lorenzo. Michael's not going to have his money in as long, but he's putting more than twice as much in, so maybe that'll help him. So his new amount is 5,000, same interest rates, but he is only going to have it in for 20 years. So again, we're going to get good at our calculators, so for our spreadsheets. Okay, I got 14,000. Did I make a mistake? 5,000, 1.056, 20 years. I think I got that right. Anyone else get 14,000?
That was 4,000.
How much did you deposit? 5,000 over 20 years. Yeah. Yeah, that'll throw it off a little bit. All right, so I'm getting 14,867, and then I guess I would call that 86 cents. $14,867.86. So even though we put more than twice as much, the more time that Lorenzo had it in there was more beneficial. Again, because the interest is collecting interest. So every year you get a little extra money, and that's going to collect extra money too. And that just keeps happening. That's why it's called compounding. They build on each other. So it's better off to put your money in as early as possible, because then time does the work for you. All right, spreadsheet time. So one thing I like about Google Sheets and other spreadsheets too is that when I have a problem that has a table in it, I can just copy and paste it. Now, I don't think it's going to benefit me to copy and paste this one, but I'm going to do it anyway. So type it. Let's see, this is homework 4.1. Do I have a 4.1 here somewhere? Or do I need to start a new one? 4.1. This was problem number 4, I think. See what it pays like. That's not too bad. All right, simple interest versus compound interest. So off to the side, I'm just going to note a couple of things. I need to know the rate I started with here. 5% and then 1,000. Oops, wrong button. There it is. Okay. Blow this up a little more. And I'll keep those dollar signs. And the word years are a problem. 1, 2, 3, 4, 5. So simple interest, how does that work? Anybody remember how I calculate simple interest? Let's put the rate in here. Sorry, I should do that. So, oh crap. Principal times rate times time, yeah. So let's see, APR here is 5%. So I'm just going to refer back to that number over there. Oh. This is years. Okay. So equals, so just the interest is going to be my principal, 1,000, times the rate, 5%, times the amount of time that goes by. And so I can just click on 1 year has gone by. Now that's just the interest. How much am I going to have? I have to add on my original amount to get that. So then I have to add the 1,000. The only catch about this formula, although I want the year to change, this purple number here, the interest rate is always in the same cell. How do I tell the spreadsheet to always look in cell E1? Put a dollar sign, yeah. And since I'm copying it up and down, that's going to change the number. So I only need a dollar sign in front of the number. Okay. If you're not sure, put it in both places and see if it works. If it works, you're good. So let's format that as dollars and fill it down. And so earlier I calculated for 3 years, it was $1,150. Okay, so here that $50 doesn't get to collect interest, right? And this 100 doesn't get to collect interest. They just give it back to me with simple interest. It's like a dividend. It's another word for that. Compound interest. What's the formula for compound interest here? What comes first? The starting amount, that's 1,000, yeah. Times, what do I do next? Elena? Compound interest, what do I do next? Not 5, just 5%, what is it? 1 plus 5%, yeah, which should be 1.05. Okay, and then what do I do with the 1.05? Raise it to the power, yeah. And here, instead of typing 1, I'm just going to grab the 1 from over there. That way, when I fill it down, it'll work nice. Ooh, I didn't reference that over there. I'll do that again in a minute. So if I hit enter here, the only thing that's changing is my power. I should be just ready to fill it down and make it dollars. And there's that 157.63. So we're a little better off because our interest collects interest. Do that one more time. Equals 1,000 times. If I want to use the rate that's on the screen, I've got to put parentheses in because I've got to go 1 plus that rate. Nice thing about that is the computer converts that to a decimal for me, which is cool. And then I can raise it to the power 1. Do I need any dollar signs to fix cells here? Yeah, E1, that's not changed. That's got to be fixed. That means I have to say, hey, don't mess with the 1 because the percentage is always in E1. And I only worry about the 1 here because I'm filling it down. And there's my numbers. So that works out nice. All right. And that right there is pretty much the same thing we had to do for Lorenzo and Michael. So I think I'll skip that one for now. Other homework questions. Homework 4.2, prep 4.2, prep 4.3 I asked you to look at last night.
There's something like
Homework 4.2, do you remember which one?
I think it's one of the longer problems. Is it that one?
Okay. Okay, let's take a look. So here, I think I just need a screenshot of the table. And a little more. Okay, so this is number 6 in homework 4.2. All right, so here, since we have a growth rate, that's our percent increase. So we're starting off here with a relative change of 1.1%, and that is the yearly growth rate. So that's per year. And we're going to have an initial population of 6.9 billion people. Since these are all referenced in billions over there, I don't have to worry about converting that to a regular number with a ton of zeros. I can just call it 6.9. Other thing that's important here is, let's see, in our formula, we're going to use a variable that's the years after 2010. Otherwise, we have to type big numbers like 2012 into our formula, which gets a little messy. So we just need to know the number of years that have gone by since we had 6.9 billion people. So variables here, P is going to be the number of people in billions. It's always a good idea to write down what your variables mean. And what's our time going to represent?
Years after.
After 2010, yeah. So important things there that it's years, not months or days. So years, and that it's after 2010. So to calculate the new number of people, I need my initial amount. What's that here again?
6.9.
That's the 6.9, yep. And then I need to multiply with an increase of 1.1%. What's that going to look like? I'm going to put that together. We're going up by 1.1%. So what's my multiplier? By an increase of 0.01, right? That 1, sorry, that's that 1.1%. What do I do with that percent increase? Add it to 100%.
Yeah.
Yeah, so that's going to give me 1.011. Yeah, so we'll always take our rates and add it to 1. So that's what we call our growth multiplier. What's the power going to be here? Number of years, that's just our T. Yeah, so that's the formula I can use. So if somebody says, well, what's going on in 2020? What would I plug in for 2020 for time? Yeah, it's 10 years later. So this is one I can put in a spreadsheet real easy. So I'm going to demo that here. I can just copy this whole chart, bring it into my Google Sheet. So let's see, this is 4.2. I'll add a sheet for world population. And then I can just come up here and paste it in. And this will be 2 years later. This will be 3 years later. 2020, Matt said, would be 10 years later. And then over here, I'm just going to take the word billions out and move it to the side. Here's where my formula goes. So it equals 6.9 times my 1.011 raised to the power, and then I just click on the year over here. And then the cool thing about it is I don't have to keep retyping it into my calculator. I just fill it down. And so I get all of the numbers, and I can just clean them up. I think they wanted 2 decimal points. So double check on your calculator right now that for, let's say, 2013, I got 7.13 billion. So see if you can make your calculator do the same thing. And your calculator could be a spreadsheet. It's the same formula every time. Starting at 6.9 billion, we multiply by 101.1%, raise it to the power however much time has gone by. Any problems getting the calculator to do that? Or your spreadsheet? No? Okay. Cool. On this problem here, they wanted us to type, I think, our formula. So P is what we're calculating. That's the 6.9 times 1.011 raised to the power of t is what they wanted there. And then the number we calculated. And here it says billion already. So again, I don't need to translate that. I would just enter the number my spreadsheet gave me, which is that 7.70 or 7.7 in this case. Yes, I know I didn't do them all. Thank you. All right, so I got those 2 right. All right, any other homework you guys wanted to go over? Is there another one, Jenna?
6.
You think 6? Okay, that was 5. I said it was 6 earlier. I lied. Okay, the chart one. Yeah, this one is interesting. So before I look at those charts right there, I'm just going to try and dissect the information that they give me right here. So let's see. I guess I can screenshot that. And then double check the questions that they're asking about. The largest group of illnesses that kids had that put them in the hospital was respiratory stuff. So here it says 1/4 of all the hospitalizations of children under 15 were for respiratory problems. And then they broke the respiratory problems into parts. And so these questions down here are just about respiratory. So for example, the first question says, okay, well, how many kids had pneumonia then in the hospital? So we're going to try and answer that next. So important information. What's the first piece of important information here?
4 million hospitalization.
That's one piece, but it's not the first important piece. There's 2.4 million kids aged under 15 were hospitalized. What's right before that? 4. Yeah, 1/4 of those, let's actually use a different color there. Red. 1/4 of those were in for respiratory diseases is what that sentence says. Okay, so right away, I'm just going to calculate that number. So if I just look at respiratory diseases, that's going to be 1/4 of that 2.4 million. And I'm going to write it as a regular number. So that would be 2,400,000. Because I think the next question they ask wants solid numbers, not in millions. So help me on a calculator. What's 1/4 of 2,400,000? $2 . 400,000. 2 million 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 400,000. 600,000? Yeah, that sounds right. All right, so of all of those 2.4 million hospitalizations of children, categorizing a child as someone under 15, 600,000 of them were respiratory illnesses. Now then those respiratory illnesses get broken up into different parts. So we've got, what else? Pneumonia is 31%. We've got, next was asthma, and that's 25%. Bronchitis, acute bronchitis, is also 25%. And then there's other kinds of respiratory illnesses like croup, that was 19%. So other respiratory is 19%. Let's see, first thing I usually ask when somebody gives me information like this is, does it add up to 100%? See, 25 and 25 is 50, 31 and 19 is 50. So yeah, that accounts for all the respiratory diseases. So they didn't leave anything out. And I think the first question we were asked was, how many kids had pneumonia? So what are we going to do to figure that out for the pneumonia? Yeah, pneumonia is 31%, so we'll take the kids that have respiratory diseases, 31% of them. So what's 31% of 600,000? 186,000, that sounds about right. So 186,000 kids roughly had pneumonia in the hospital in 2005. So the trick there was I had to incorporate that. I had to note that because only a quarter of them had respiratory. So it's a quarter of the 2.4 million, and then 31% of those had pneumonia. So that was the first tricky part. The next tricky part was looking at those graphs and trying to figure out which is the right one. So help me do that. I found that a bit difficult myself. Any more? It's not getting any bigger. All right. All right, so let's see. Which two are the same? Bronchitis and asthma were both 25%, right? So we're looking for a chart that has bronchitis and asthma as the same size pie. Pneumonia is bigger than everything, and other is smaller than everything. A, pneumonia is bigger than everything. Other is a little smaller. And it looks like bronchitis and asthma take up exactly half of the graph there. Yeah, I like that, Aaron. Okay, so I'm leaning toward A2. Can we rule out other stuff? Asthma and bronchitis, do they take up half the graph here? No, so that one's out. Do they take up half the graph here?
Yeah.
Yeah. Ooh, they're not the same. Asthma is bigger than bronchitis here. Yeah. Okay, so B and C are out, and A is the winner. All right. Yeah, so it took me having to go back and forth with different aspects of their percentages to try and figure that out. Let's see, we figured, what was this, 186,000? And do we get 2 green lights? Yes, nice. All right, any other homework problem you want to play with? Not at the moment. Okay, so I was hoping you guys would look at the prep for 4.3 last night. I talked a little bit about 4.3 yesterday. Let's take a look at that right now. And so basically this stuff here is kind of like review of stuff we've already done. So let's see if everyone can whip out this problem right now. A vehicle was purchased for $22,400. It's depreciating at a constant rate of 4%. Okay, and let's assume that's 4% per year. Determine the approximate value of the vehicle 11 years after the purchase. So see if you can whip that out on your calculator. I would write something on paper first. What is this car going to be worth in 11 years
given its starting value and its rate of depreciation. Screenshot that in here so I can blow it up a touch. And we want to the nearest whole dollar, not dollars and cents.
So for my formula, what do I want to multiply by? 96%, 4%, or 104%? We have a bunch of different answers. What's it going to be? Is the rate rising or falling? Okay, it's falling, so that means I got to take away from 100%. And whenever we do our multiplication, the quick way is to always deal with 1 first. So I'm going to take 4% from 100%. That means my multiplier is 96%. And that gets raised to whatever power time that I need. So this is the general formula. I just want to figure out what's going on in 11 years next. So 11 years is going to be, take that 22,400, multiply by 0.96 to the power of 11. That should give us what we want.
So let's see what a calculator thinks about that. My calculator says I made a mistake. What did I do wrong? Oh, I have an extra 0? Oh, yeah. That. 14,297 to the nearest dollar. Okay, so we gotta, this is a place where, again, we gotta be masters of our calculator. Every calculator works a little different. All right, let's try another. Anybody have a question about my setup on that one? This was number 1, yeah. And on these, if you're just sitting at your computer and just thinking it and whipping out your calculator, you're cheating yourself. Write some stuff down. Please write some stuff down. Notice I wrote all that stuff down. That's just to make sure I'm doing it right. Otherwise, it's guess and check. I try something, I hit submit. It says no. I try something else, I hit submit. Not a good learning strategy. Doesn't pay off on a test later on. All right, let's try one more of those, and we'll talk a little bit more about 4.3. How about this one right here? I'm going to copy this. Now we can just do it right here. So what we want to do is we want to identify what power should we have here so that we end up with the number on the other side. So what power would we raise 10 to get 1,000? Not 2, 10 to the second, that'd be 10 times 10 or 100. Third power, yeah, and check on your calculator. 10 to the third power. That's a 1 with 3 zeros. All right, so here I have 100,000. How many zeros are there? 5 zeros. So this should be 10 to the 5th power. Double check on your calculator. What do you think about the next one? 10 to what power is 0.001? Got a -2 as a possibility. -3 is another possibility. Plug those into your calculator. Which one seems to work better? -3. So just to double check, if reading this as 0.001 is slang. It's like saying ain't. The proper way to read that is to identify the place values. That's tenths, hundredths, thousandths. So this would be 1,000th. 1,000 is 10 to the third. So this must be 10 to the negative third on that one. And this down here would have to be what? 10 to the negative 2? All right, so we just calculated the exponents, correct? What's another word for exponent? Starts with an L. Logarithm. So just for fun, on your calculator, what is the log of 0.001? It's going to be -3, yeah, right? Just double check. I can even go into Google and type log 0.001, and Google is going to write back and say, hey, it's -3. Hit enter if you want. It's still going to be -3. Bang, there it is. So when we identify what an exponent should be to get a certain answer, that's a logarithm. That's all a logarithm is. So I'm just going to write that down for fun. Logarithm. What does logarithm mean again? It just means exponent, yeah. So that's the simple part of it. The tricky part is writing down a logarithm equation based on an exponent equation. So for example, I had 10 to what power was 1,000. The reverse of that equation would be to take the power out. A power is a logarithm, so I write log. Then I write my target value in parentheses. And I like to write what the base is. So an exponent has a base. A logarithm is an exponent, so it should always have a base too. Even though the calculator button doesn't usually show it, we should put it in there. Okay. And our calculator, this is the same thing as saying log of 1,000. It's going to tell us 3 is the answer. Let's do one more of those, and then I'll hand out that activity, because I don't think I handed it out yesterday, did I? 4, 3? No, okay. So let's suppose we're playing with 2 as the base. I want to know what power I can raise 2 to get 1,000. What I need you to do is, before we whip out our calculators, what is the way to write this down in terms of logarithms? So I want to know what x is. What does x have to equal? It's a log, because it is the power. Yeah, power is equals a log. Okay. What's the base of this logarithm here? What's the base of the exponent? 2. So the 2 just slides kind of like underneath right there. And then I put a parentheses and I write my target. What's my target? 1,000. All right. Now the calculator does not have a log base 2 button, so I have to trick it. Does anybody remember the trick on how to use log base 10 to make this happen? Divide by log of the base I prefer. Yeah, so I'd have to divide by log of 2. Okay. So see if you can make your calculator tell us what the power should be here based on that version of using logs. And give me 3 decimal places on that. What do you think, Jenna? 9.965. Oops, 965. Okay. Jenna was unsure of that answer, which is okay. Matt, you like that number? Okay. So I was thinking, so in computers use what's called binary number system, which is based on 2s. So I'm kind of familiar with a lot of 2 to whatever power. And I know 2 to the 10th power is 1,024. So I'm thinking it's got to be a little less than 10. Okay. So nailed it. Now double check. Take 2 to the power, 9.965. We won't get exactly 1,000 because we rounded, but we should get close to 1,000. $999.5. That's close to 1,000. If you want closer, throw more decimals in your calculation. All right, so we are officially done with Fun for Math. I'm going to send your worksheet to the printer so you can take a look at it for homework. And we will play more with 4-3 tomorrow.